Welcome to my talk on implementing distributed consensus. Quick disclaimer, this work is not affiliated with any company, including Google, the company I currently work for. This talk is a result of a personal education project of mine. What is this about? This is about my hobby project. I implemented distributed consensus, something I read about in the Paxos papers. Paxos is one popular distributed consensus protocol. And along the way, I learned a lot about how computers reach consensus, and this talk is basically a fine selection of some of the mistakes I made. I used Go as a language, but the code should be readable for enthusiasts of other languages. I rely on some of the Go features, but similar features exist in other languages. What is distributed consensus? This is me and my friend Kim, when we were kids. One day, Kim brought a hot potato to one of our playdates, and Kim liked to invent new games. Kim's hot potato game was very simple. There was only one rule: don't ever drop the potato. Unsurprisingly, holding a hot potato wasn't much fun, so whenever someone ended up holding the hot potato, they needed to find someone else to hold it for them. Meet Little Peter. Little Peter is Kim's little brother. Little Peter liked to join us when we were playing. How convenient. Now Little Peter holds the hot potato and needs to find someone to hold it. Remember, you're not allowed to drop the hot potato, ever. Over time, the hot potato game became famous, more friends joined in, and soon hundreds of people were playing the hot potato game. At some point, having a physical potato was no longer suitable, so we modernized our game. The game became fully digital. Players connected to a hot potato game server over the internet and threw each other the hot potato. The hot potato game server kept track of who holds the potato. The game server kept the state, so to say. The game server was the single source of truth for the hot potato game. But there was a problem with that architecture. Remember, we are not allowed to drop the hot potato ever. We can't trust such an important game state to a single server. Servers occasionally need to go down for maintenance, or servers can burst into flames. That happened. A single server cannot be trusted. We need more servers, so we scaled the game up to 5 servers. Same potato on 5 game server instances. Now that we have 5 hot potato game servers, we have new problems. Every server needs to know who holds the potato. We need distributed state. We need distributed consensus on all state changes that occur in the game. And when the game changes, or when the game state changes, it should change so for all servers. You can think of the hot potato as a lock, and the hot potato game servers reaching a distributed consensus on who holds the lock. One might call it a distributed lock service. Popular protocols to achieve distributed consensus include Paxos, which comes in the variants of multi-Paxos, cheap Paxos. There's also Raft, which has been popular. Zookeper Atomic Broadcast is another one. Distributed state or distributed consensus is also core of proof of work systems like Bitcoin. And my favorite lock protocol is the lockstep anti-cheating in Age of Empires. There are a couple of implementations. There's a Chubby by Google. It's a coarse-grained lock service. There exists a paper that goes into details. etcd, which is a distributed key value store, I think most popular for its use within Kubernetes. And Apache Zookeper, a centralized service for maintaining configuration information, naming, and providing distributed synchronization. New kid on the block is Skinny. Let me introduce Skinny, which is a Paxos-based, minimalistic educational lock service. Skinny has a lot of features, but these features are kind of non-features. Skinny is designed to be easy to understand. It is relatively easy to observe, so it populates a lot about its internal state. It has coalesced roles, so that means different Paxos roles are coalesced into one binary. It has a single lock. So that provides one single lock. There's one state that can be changed, but it is not multi-tenancy or multi-lock or multi-state. And locks are always advisory. So that means if someone is taking the lock from the distributed lock service, there's no way for the lock service to enforce that the service handles it correctly. It is written in Go. It uses protocol buffers. It uses gRPC for transport. And please do not ever use it in production. It is a purely educational service. It is not production ready. Skinny lives in a repository on GitHub, where you can find documentation, the source code, and examples on how to run your own Skinny quorum. Talking about quorum, in this talk we'll be using a so-called white quorum with instances in Oregon, Sao Paulo, London, Taiwan, and Sydney. This is very unusual in practice. Like in the real world, we would not want to have a global white quorum because that gives us terrible latency when we are jumping continents with our information. It is, however, pretty nice for observation and learning. The longer the distance, the more likely we see timeouts, we see deadlines exceeded, and we see latency that is, in some cases, big enough so that we can observe with the human eye what is happening. Next, let's look into how Skinny reaches consensus. We can see here our Skinny quorum, and a quorum is a group of Skinny instances. You can think of it as binaries of the server running in a data center, and each of these data centers is on a different continent. So this is our global quorum of instances. And what happens now is that Beaver comes along, and Beaver talks to the instances that is most closely to Beaver, and Beaver wants to acquire the lock. So this group of instances, this quorum, now needs to find a global state where everyone can agree on if Beaver or not should have the lock. And for that we need some internal state for each instance, and this internal state needs to be synchronized over all of the instances. So how that looks like is that each of the instances has 3 fields. One is ID, and ID is something like a round number. So each time these talk to each other, they attach an ID to the message, and this ID keeps increasing. It's very important. We just need to remember at this point, there's an ID and it's always increasing. There's also a field called promised, and promised holds the ID of the next round in which a value may be promised. And then there's a field called holder, and holder is the name of who currently holds the lock. Remember, Skinny just provides one single lock. So in a distributed lock service that provides multiple locks, holder would maybe an array or a slice or some other data structure. Here it is just a single string holding field. So Beaver asked for getting the lock, and that resulted in the instance number 1 changing its internal state for promised to 1. And then it is sending out a proposal. And the proposal has the ID 1, because that is the ID plus 1. We are always increasing the ID. And what happens now is that all of the instances compare the proposal ID with their own ID. And if the proposal ID is higher, then that means we are talking about a new future state, which they're interested in knowing about. And so what they do is they promise that the next state with the ID 1 is something that they would be okay with, because they all have IDs which are lower than 1. And they send back messages which tell the instance number 1, I'm going to promise you if there is a state change attached to an ID 1, that this is something I can agree with. Because my last state, ID 0, is lower than 1, and that means whatever the new state is, I'm happy to also learn that state. And that means for the instance number 1 that it can now increase its own ID. So it has been promised that a new round of messages that would have the ID number 1 is likely to go through. And for its internal state for holder, it sets beaver, because instance number 1 wants to give the log to beaver. And then it sends out commit messages to all the other instances, saying ID number 1, that is the one that you promised me before, please commit to have the value for holder be beaver. And for all the instances, they see this message coming in, ID number 1, that matches what they promised, so there's no conflict there, and they happily copy over the state for the holder, and everyone now believes that beaver is the holder of the log. So that means all over the world, globally, each of these instances have a shared state for who is holder, and that is beaver. Out of courtesy, they send commit messages. This is not technically required, but it speeds up things a bit, and it's also nice to say if you committed to something. For instance number 1, this now means beaver has the log. Everyone globally agrees on that. So instance number 1 talks back to beaver and lets beaver know that you have the log. Congratulations. So far this all went well, and what we did not see yet is what happens when something fails. This is where we really want to have distributed consensus, so that if a server goes down, we still have state. For example, in our hot potato game, if an instance goes down, we can still play the hot potato game. It adds a resilience to our systems. So join me once again for another round. We are currently at ID number 9, and the log holder is beaver. So we have had a couple of state changes, and currently, once again, beaver is the holder of the log, and the quorum agrees on that. And what now happens is 1 or 2 data centers burn down, like they do every now and then. And now we have only 3 instances in a quorum of 5. 3 is still a majority, so that means we are still good. So an engineer comes and fixes the data centers, servers come back up, but the state is lost. So now we have again a quorum of 5, but 2 of the instances have no idea what happened. They have no memories of the past. They're starting blank. And as it so happens, Alien comes along, and Alien also wants to acquire the log. And Alien asks one of the instances which have no previous state. The instance increases the ID by 3, so each instance increases their ID by a different number, so that helps keep everything going and preventing loops. And the promised state for instance number 3 is also 3, because instance number 3 believes that ID number 3 will succeed. But first it has to go through the proposal stage, like all the instances. So instance number 3 sends out proposals. How about a new round number? What about ID 3? Can everyone agree? And what happens with instance number 5, seeing only ID 0, because it started with a blank state itself, it thinks, yeah, 3 is a new round number that is higher than my current round number. That sounds good to me. So I promise you, ID number 3, I'm in. But the other instances, they still hold state about a previous reached consensus. So they can't promise that. And they're letting the instance number 3 know, actually, we are already at ID number 9, so number 3 not going to work for us. And by the way, holder is currently beaver. You might want to update your state. And that is exactly what happens. Instance number 3 learns that the holder is beaver. So no longer alien, it is beaver. It also learns that we are already at ID number 9. So what it does now, as it has learned that there was a previous state, it sends out a new promise. So it takes 9, increases it by 3 because it is instance number 3, and sends out new proposals. How about ID 12? Can we agree on that? And that is something everyone can agree on, because I12 is higher than 9 and is higher than 3 and is higher than whatever state there was before. So everyone is promising, yeah, sure, ID number 12, that's something we can work with. And what happens then is that instance number 3 now knows that ID 12 would go through, and it starts committing with ID number 12 a new value. And that value is not alien, it is beaver. It is beaver because the instance number 3 learned previously there was consensus on beaver holding the lock. And with this new round of commitments, all instances are now back on the same ID, on the same holder, and that holder is beaver. We have once again, even after failure of 2 instances, reached global consensus on who holds the lock. The instances update their internal state, just it's a new ID number 12 for most of them. For instance number 5, it is not only new ID 12, it also is a new value for holder. And they send out of courtesy commit messages. And then instance number 3 gets back to alien and lets alien know, unfortunately, you have not acquired the lock, holder is beaver. And alien, like any good application, does not rely on having the lock and hopefully does not mess with global consistency in a database or whatever alien wanted to have the lock for. We have seen Skinny in action, we have seen Skinny when everything is fine, and we have seen how Skinny deals with instance failure. And next I want to go into the implementation part. So what does it look like under the hood? We have a couple of APIs. We see the quorum here again. We have 5 instances, and one of the APIs is the lock API. And the lock API is used by clients to acquire or release a lock. Then we have the consensus API. The consensus API is used by Skinny instances to talk to each other and to reach consensus. So think of the proposal and commit messages. There's a third API, a bit less important. It is the control API. And what it is used for, it is used for everyone working with Skinny to observe the internal state of the instances. So this is more a monitoring thing, if you will, and since this is an educational log service, it also helps understand what happens, or if something is broken or something is wrongly optimized, which happened to me, then you can debug a bit the instances. Let's look into the details. First, the log API. It contains 2 messages. One is the acquire request with a string holder, that is a client wanting to acquire the log, and an acquire response, that is a boolean whether or not the log has been acquired and who the current holder is, which could be different from the one who wanted to acquire the log. There's another message flow, and that is a release request where a client can release a log and gets back a boolean or whether or not that worked. And these acquire and release actions are part of a service called log. The consensus API is a bit more complex. It has a promise message and promise response for the first flow in each round, and the promise request contains an ID, which is an unsigned integer 64, and the response contains a boolean whether or not an ID number has been promised, and an ID, and also a string holder, and that contains any previously learned holder. We have seen this in the examples with the instances failing, that one instance reported back in the promise response, hey, there was previously consensus that Beaver holds the log, so I can't promise the new round. Then there's the commit request and commit response message, and the commit requests contains the ID and the new value for a holder, and the response message just contains a boolean whether or not an instance committed to it. And they're both wrapped in the consensus service. So they're promise and commit here. The control API is really simple, used by admins to see the internal state. They have an empty message that requests the status and a response that basically throws out everything that we have that could be of interest. The name of the instance, the configured value for increment, like what is the number, then the increment that we attach to each ID, a timeout, whether or not what the current promised round number is, the ID, what the current round number is, what the current holder is, and a list of peers that this instance is connected to or wants to connect to. And this all is in a very simple service that can just report the status. When I was implementing this, I made some interesting learning opportunities. And I'm going to let you know in case you ever need to re-implement distributed consensus. My advice would be not to, but it is a nice learning opportunity. First thing is reaching out. So one instance talking to another instance or to a list of peers. How does that work? We have an instance, and there's a data struct representing the instance. And in that we have a list of peers. So these are all the other instances in the quorum. So remember, each instance needs to talk to each other instance, and that means each instance needs to have a list of peers that it can talk to. And these are basically gRPC client connections. Here's a list of peers. And here is the client connection that we hold for each. And then we have a propose function. And in that propose function, we send proposals to all peers. So we have this list that we just talked about, and for each item in that list, we send a proposal out. And then when we get the proposals back, or the promises back, then we count all the cases in which the new round number was promised. So here's us reaching out, and here's where we count the responses. And there's also a function to learn any previously agreed consensus results, but we're not going into detail of that. So this is just learn response, and we just assume it is there and it works. So this piece of code results in the following behavior. We have sequential requests, and we are waiting for I/O. So we send out the proposal number 1, we count, and we may learn, and then we send the next one, and the next one, and the next one. If an instance is slow or down, it looks like this. We send out the proposal, we send out the second proposal, and then the third one is really, really slow, and that means a lot of time is wasted waiting on I/O. And that is because we go through the list sequentially. So the first improvement that we could make when implementing distributed consensus would be to limit the waiting for I/O. So how about we do this? That after a while, if an instance is just slow and not responding, we just cancel the request and continue with the next one. That should give us a bit more reliability. And we do this by adding timeouts. So we have this context, which is a Go language feature that gives certain constraints to functions, especially network operations that we call. And here we have a 3-second timeout. Although this value is configurable, if you're playing around with Skinny, you can set this value to something that you like. And we also have to cancel the context, that is to prevent context leaks. The next improvement that we can make is that we have concurrent requests. So right now we are sending out one request after the other, and we are canceling them if they're taking too long. So what we want to do now is we want to send out all the proposals quickly one after the other and have them all wait for I/O at the same time. And then once everything is back in, we synchronize the counting and we synchronize the learning. So once we have all the responses or the requests have failed, we count if we have enough promises to proceed, and we learn any previously learned value if there had been any. Concurrency in Go is most often achieved by Go routines, but you can implement this in most other languages by using threads or any other language-specific features. And what we do here is that we go over the list with a for loop, and then for each item in the list, we fire up its own function, a bit like a thread maybe. And we have a context with timeout again. So that means although they're all working concurrently, we're still adhering to a timeout. So we don't want some of the requests to take very long. But now what? Now that we have these all going, how do we synchronize on all the results? And this is where we have to define a new data structure to make that work, and that is the data structure response. It contains a string from who the response is. This is mostly for logging purposes. It contains a boolean, whether or not something has been promised, the ID, and the holder. These are basically representations of what is in the response, in the promise response message anyway. And we use a channel, another Go feature, but there exists similar things in other languages. And the channel is something where we can throw in a couple of items, and then we can, from all of the Go routines, and then we can read them in a new Go routine where we just read from the channel and in this case start counting the results. So what happens is that we go over the list of peers and we fire up the function, and the function goes and sends out the proposals, and then they come back, and then we throw a response data structure filled out with what we got back from the peer into the responses channel. And then we start with blank values for yeah and nay, for yes and no. And we start with yes with 1 because we are in one of the instances, and when an instance sends out a proposal, it always promises to itself. So this is why we start with 1 for yay and 0 for nay. And then we go over the responses, which are in the responses channel. And if it has been promised, then we increment yeah, and if not, then we increment nay. And then there could be something to learn in each of the responses, and this is why we also call the learn function here. So the learn function is called the same number of times that we have peers like before, but now it is called later when we read the responses. A lot of synchronization going on here. But something is wrong. What's wrong? Can you spot it? So here we are opening a channel, but we did not close the channel. And that is another Go thing. If we open a channel and then later read from the channel in a loop, and we do this here, then we need to close the channel because this range is blocking forever until the channel is closed. So to do that, we need even more synchronization. Because remember, all of this is happening somewhat at the same time, concurrently. And for that, we use a wait group that is a bit like a semaphore. It's a synchronization tool. And that means when we have all the responses back, either because the peer replied or because we ran into a timeout and canceled the outreach, each time when all this has been done, the wait group should have a value of 0. And there's then this function that runs concurrently, and that just blocks until the wait group has the value 0. And when it has that, it closes the channel. The result of that, we have all the proposals going out more or less at the same time. And as the answers come in, as the replies get in, we count and we learn any new values if there are any. So that's nice. I think we optimized the outreach quite a bit. Next thing I want to talk about is ignorance bliss? And that is early stopping. So remember, we have this quorum of 5, and we want to achieve a global consensus. And that means we have to have the same state in the majority of the instances. Even if not all instances agree, at the moment we have a majority, there cannot be any other state, because the minority cannot reach consensus. So that means if we have an instance that is slow and not responding correctly, maybe it takes too long, it runs into timeouts all the time, we could still reach consensus. And we could do this even faster than we do currently. So we are reaching out, proposing to a couple of other instances, and we start the counting and we start the learning as the responses come back in. So here's one response, we are now at 2. And here comes in another one, and we are now at 3. And in a quorum of 5, 3 is a majority. And that means right now we can cancel the other 2 outreaches, and we don't have to wait for the responses because we have reached majority. And majority in a quorum means consensus. So how do we implement early stopping? The first thing is we had a context for each outreach, and we are now switching it to one global context. So we have now one context, and we reuse it each time we reach out to another peer. So that means as soon as we have a majority, we can cancel that one context, and it cancels all the current in-flight outreaches or responses or whatever the state of each of these connections currently is in. And we always cancel the context before we leave the function to prevent context leaks. Again, not the most important part here. So this all looks the same. The context is now the one that we inherited from globally. But here it gets interesting. The error handling. So we don't care about cancelled contexts anymore. If a context has been cancelled, then that means no one is interested in our result anymore. We are not going to read the response. We are not interested in any of this. We just return, and that's it. We don't want to waste any more compute on something nobody is interested in anymore. And if there was an error, but it was not a cancelled context, maybe it was a timeout or any other error that happened, we want to make sure that this is cancelled as a negative answer. So this helps us not only quickly finding out if we have a majority for something, but we also might quickly find a majority against reaching consensus. So this is why it's important for us to also count all the negative answers. And so if there's any other error that is not the cancel context, we're going to send a more or less empty response data structure into the responses channel. and that means it has the default value for Boolean, and that is negative in this language, and that means we will count it as a negative answer. And for the early stopping, we need to close the response channel once we have all the answers we need, or everything has been cancelled. And that just works like it worked before, no changes there. But when it comes to counting the votes and to cancelling the global context, there are some changes. So first, when we read from the responses channel, we count the votes as we did before, and we also learn about any previous state if there has been any. But also we check for whether or not we have a majority already for positive answers or for negative answers. It doesn't matter which one. As soon as we have a majority, we cancel the global context, and that's it. So, is this fine what we are doing? Because now timeouts are even more critical. And when I implemented that and I set pretty tight timeouts, I was getting faster consensus. But when I looked into the instances, I saw that there were two instances actually that were never ever getting the state, because the timeouts were always hitting before these instances, slow as they were able to learn that. And I call this effect the ghost quorum. So with our early stopping optimization, we are also opening the gates for something harder to debug, and this is this ghost quorum. And the reason was a too tight timeout. So it's always the same instances who time out, and that means that they're technically not really part of the quorum anymore. So instead of a quorum of 5, I had a quorum of 3. And this is a hidden reliability risk. So if one of the remaining instances, one of the 3 that were always responding, fails, basically the distributed log service is down. Because of the timeouts, the other 2 are also not really reachable in practice, and that means we cannot reach a majority anymore, and that means we cannot reach consensus anymore. So this is what happens when one of the healthy instances goes down and the other 2 aren't really there. We have this kind of a ghost quorum, and these 2 will never reach a majority in a quorum of 5. So that's a risk one needs to be aware of when optimizing around early stopping and timeouts. And that's how I implemented distributed consensus. My sources were the Paxos paper, Reaching Agreement in the Presence of Faults by Leslie Lamport. I found the Chubby log service for loosely coupled distributed systems paper. Very interesting to see how that works. I read this before I was able to see it from the inside, and I really liked the paper. Then there's this great video about Paxos agreement by Dr. Heidi Howard, and I watched it 100 of times minimum to understand how this works and to check my implementations against the theory, how they should work. There's also a talk by my colleague Luis Cressida Torres about the Paxos algorithm that is also worth watching and learning about Paxos. And then, of course, the Skinny distributed log server is open source software. It is written exactly for this purpose, for learning about distributed consensus. It has code comments wherever I thought it might be helpful to comment on the code. It has only the necessary things. There's no more than necessary in there, hoping that it is most helpful. It comes with Terraform modules and Ansible playbooks. They may or may not work in your setup, but if they work, you can quickly set up a global quorum distributed over 5 continents to play with. And you can find me on Twitter, where I tweet about SRE and technology, and I also have a blog. Thank you.